Start recording. Today we have what's called conditional and absolute convergence. So if we have absolute convergence, for example on this one, on the very top there, if we put them in order, if we put the terms in order, this is converging to 2/3. If we rearrange them, no matter how we rearrange them, it'll converge to 2/3. Doesn't matter. With conditional convergence, if we, let's say, put them in order, plugging 1 in, plugging 2 in, and so on, this will converge to the natural log of 2. If we use the same terms but rearrange them, you could put them in an order that would not converge to natural log of 2. This order would converge to natural log of 2 square root of 2. And not only could you have it converge to that, if you knew the pattern, if you knew how to rearrange them, you could make it converge to anything you want if the series is conditionally convergent. Now, I've never done that. Even in my undergrad at UNL, in my graduate work at Wayne, I never did this. So this is way beyond the scope of this class to actually find out how to do that, but just know that's what conditional convergence means. Theorem, if the series, the absolute value, converges, then the original also converges. We'll talk about that. The series is absolutely convergent if the absolute value of the sequence converges. If the series converges when we take the absolute value. The series is conditionally convergent if the series converges but the absolute value diverges. All right, what does all this mean? Here we go. Let's put it into practice. Determine whether the given alternating series converges or diverges. If it converges, determine whether it is absolutely convergent or conditionally convergent. First of all, we have to have an alternating series to determine whether it's absolute or conditional. If it's not alternating, then if it's convergent, it's absolutely convergent because we don't have to worry about these positives and negatives. So our first step is to remove the fact that it's alternating. Take the absolute value of this, which means everything becomes positive. So n equals 1 to infinity of 1 over square root of n. So there's the brand new problem. And we ignore the one that we just had. We ignore it. We forget that it's there. So we got this brand new problem. On this one, I'd say p is equal to 1/2. That's less than 1. This diverges by p series. Test. Now that we decide, well, now it diverges absolutely, now we go back to the original and see if it converges conditionally or it might just altogether diverge. So we're going to do the alternating series test here. Limit as n approaches infinity of 1 over square root of n is equal to 0. And then I have to be able to say this. 1 over square root of n plus 1 is always less than 1 over square root of n. That's actually true. I have no problem saying that, because the only variable we have is in the denominator. So that's definitely going to be true. So this converges conditionally by the alternating series test. So it does converge, just not absolutely, conditionally. All right, well, now we just do the same thing, but we have to maybe use different tests. And then we got to talk about, well, what happens if it converges absolutely like this one does? So let's get rid of let's take the absolute value. I was going to say, let's get rid of the negatives. That leaves 1 over 3 to the n. And this is geometric. So r is equal to 1/3. The absolute value of 1/3 is less than 1. So this converges absolutely by geometric series. And the good news is we're done with it, because if it converges absolutely, then the original would also converge. So we don't have to do anything else. We like it when it converges absolutely, because then we're just done. When it diverges absolutely, then we got to go back and reevaluate. Determine if the series is absolutely, well, same instructions. So let's look at this one. This is the alternating harmonic series. So let's get rid of the negatives. Let's take the absolute value. And we get 1 over n. And we can say diverges by harmonic series. Don't have to show any work for it. And we don't have to show it now. Now that it diverges absolutely, we go back to the original and we can say that this converges conditionally by the alternating harmonic series. So for that one, we don't really have to show any work. AP is okay with you writing stuff about harmonic and the alternating harmonic series. But now we found out it converges conditionally, not absolutely. Well, I had one where it's 1 over 3 to n, so I thought, well, what happens if we throw this n in here, where it's not geometric when we take the absolute value? So we're going to do absolute value, n equals 1 to infinity of 1 over n3 to the n. Well, what are we going to use to, what test are we going to use here? What do you think? What does it look like? Yeah, it's a ratio test on this one. So we have the limit as n approaches infinity, absolute value of 1 over n plus 1, 3 to the n plus 1, times n3 to the n over 1. Limit as n approaches infinity of, let's see, we have an extra 3 on the bottom. So n over n plus 1 times 1/3. That ends up being the absolute value of 1/3, which is less than 1. So converges absolutely by the ratio test. Now we don't have to go back to the original. If it converges absolutely, the original converges. No problem. On this one, do I have one down below or is that it? Oh, I got one. Oh, I know. Yeah, that's one's going to be, that'll go quick. Let's take the absolute value. Same instructions, by the way. N equals 1 to infinity of 1 plus n over n squared. And this one, I don't know. I wouldn't use ratio test because it's going to equal 1 if we do the ratio test. It's not geometric. Not p-series. It's not simple enough. So limit comparison test is one we're going to use for this. Now, if it was like 1 over n squared, we could use p-series, but we could also use direct comparison test. Direct comparison has to be much simpler than this one. So we're going to compare this to n equals 1 to infinity of 1 over n, or n over n squared, reduces. This diverges by harmonic series. And now, pretty sure this is going to diverge, but we have to we got to keep going. Limit as n approaches infinity of 1 plus n over n squared divided by 1 over n, or multiplied by n over 1. That's equal to 1, which is finite and positive. And if that happens, they diverge together or converge together. So diverges by limit comparison test. Well, that's a bummer because now we have to go back to the original and use alternating series test. So the limit as n approaches infinity of 1 plus n over n squared is equal to 0. So it has to pass the nth term test. Well, now we have to be able to say 1 plus n plus 1 over n plus 1 squared is less than 1 plus n over n squared for n greater than or equal to something. And we have to write that for n greater than or equal to something because it's just too complicated to know that it decreases right away. It may not. It has to eventually decrease. So this one's a little bit too complicated to just be confident with this statement. We're going to take the derivative and show that it eventually this decreases. So f prime of x is bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom over the bottom squared. So again, when you square the denominator, that's built into the derivative of a rational. It's going to be squared, so it's always going to be positive. We're just looking at the top. I literally totally lost track of what I was saying. 2x squared over x to the fourth. So negative 2x minus x squared over x to the fourth. So we only care about the top as far as the signs are concerned. So negative 2x minus x squared, we want that to be less than 0. But we got this extra x. We're going to do this a little different way. We know that this is a parabola, an upside down parabola as a matter of fact. So if we take out an x, we get negative 2 minus x. Has to be less than 0. So the zeros are 0 and actually negative 2. That's what makes that 0. So the zeros are 0 and negative 2, and it's kind of this upside down parabola. Well, it turns out that this is 0 at 0 and then decreases after that. It's the derivative is negative after 0. So I'm going to go back up here and look. The series starts at 1. So I really don't have to say for greater than or equal to. As a matter of fact, it's not equal to. It's not negative at 0. It's 0 at 0. So I'll say greater than or equal to 1. But that's where we're starting the series anyway, so it all works out perfect. So because I can say these two statements with a little help from a derivative, converges conditionally by alternating series test. So that's probably the one that has the most work on it. You'd have to do the most on that. That would be the longest one there, just because of that derivative stuff. Any questions? This last one here, I just want to show that this right here causes this to alternate. Because if you plug 1 in, you get cosine of pi is negative 1 over 1, 3 to the 1, right? Plug 2 in, cosine of 2 pi is positive 1 over 2 times 3 squared, minus 1 over 3 times 3 to the third, plus keep on going. So rather than writing it like this, I could write it like this. N equals 1 to infinity of, let's see, negative 1 to the, I need the first one to be negative, but if I put that to the first, it will be over n 3 to the n. And we already did the work for that because it turns into this right here, except this says n plus 1, but it's still alternating. It doesn't matter. So I really don't want to finish this one. All I want to do is show you that is another way to write an alternating series, which looks like it's disguised. It's like this secret. It's not a secret, it's just alternating. That's it as far as the new stuff. It's just barely new in that you create this brand new problem, evaluate it, see if it diverges or converges. If it diverges, then you got to go back to the original and eventually say it either diverges or converges conditionally. So you make this brand new problem. All right, if you're watching this at home, go ahead and fast forward if you'd like, or give this a try. I want you to give this a try. This is now practice. This isn't new stuff. As a matter of fact, I don't think conditional and absolute's on here at all. I'm kind of changing gears on you. Help each other out. When you're supposed to find the radius of convergence, there's not a whole lot of things that will lend itself to that process. The only two things that we really have are the ratio test, and because that has absolute value in it, and the other thing is if it happened to be geometric, which I don't think this starts out as geometric. So we're looking at ratio test almost every time, unless it happens to be geometric. So letter A, we're going to do the ratio test. Limit n approaches infinity, absolute value of, let's go with 2 to the n plus 1 over n plus 1 and x minus 1 to the n plus 1. But then times n over 2 to the n, x minus 1 to the n. So limit as n approaches infinity. Absolute value of, there's an extra 2 on top, extra x minus 1, and then n over n plus 1. So that ends up being absolute value of 2 times x minus 1. Now we want that to be less than 1, so negative 1 less than 2, x minus 1 less than 1. So negative 1/2 less than x minus 1 less than 1/2. And that's what they're talking about. They're saying find the r when you're centered at 1. So we're centered at 1. The radius, or r, is equal to 1/2. All right, try letter B. All right, says find the first 3 non-zero terms in the general term of the Taylor series for f prime, the derivative f about x equals 1. Maybe I can actually fit it over here. B, let's see. Plug 1 in, get a positive, so 2 times x minus 1. Plug 2 in, that's going to be a negative. 2 squared is 4 over 2, x minus 1 squared. And then plus 2 to the third, 8 over 3, x minus 1 to the third, minus keep on going. And I want to actually discourage you from simplifying too much. Because sometimes simplifying breaks, it kind of ruins the pattern that's happening. So it says f prime. All right, so f prime of x would be 2 minus 4 times x minus 1 plus 8 times x minus 1 squared minus keep on going. So the general term would be 2, oh, let's go negative. I'm good at forgetting that. Negative 1 to something. Well, now I decide, do I want to start with 0 or 1? I think I want to start with 0, but it wouldn't matter. So if I start with 0, I can make that n, because it's positive to begin with. Then I just got to make this 2 to the n plus 1, because I want that power to start out as 1. And then it's okay to have x minus 1 to the n, because I want that power to be 0 right away. So like I've said the whole chapter, just make it match. You can pick either one, just make it match. See, the Taylor series for f prime about x equals 1 found in part B is a geometric series. Find the function f prime to which the series converges. How many functions do you know? 1. You only know 1. So f prime, well, let's do this. Let's say a sub 1 is 2, but the r is negative 2 x minus 1. So it's negative because it's alternating. So it starts out as 2, then you multiply by 2. It happens to be negative 2. So they're saying f prime of x, we took the derivative, has a function that goes along with it. It's a sub 1 over 1 minus r. So I'll just put it right away as a plus, because they have minus minus. A sub 1 over 1 minus r. Let's simplify. 2 over 1 plus 2x minus 2. So 2 over 2x minus 1. 1 minus 2 being negative 1. So we did the first 2 sentences. They talk about how it's geometric and then find the function to which the series converges. What's the next 3 words that people usually skip? Use this function. Don't go up to the series. It's not saying use the series. It says use this function to determine f. Well, if we have f prime, how are we going to find f? Integrate, right? All right, so we got to integrate this. So f of x is going to be the integral of 2 over 2x minus 1 dx. Well, now we got to dig into our tools for integration. What are we going to use? Use substitution, right? Do you see a function and its derivative? I do. All right? So we're going to go u is equal to 2x minus 1. du is 2 dx. So this becomes the integral of 1 over u du. It's not only is it substitution, but we hardly had to alter it at all, because we have exactly what we need. So this is the natural log of the absolute value of u, but u is 2x minus 1 plus c. Well, if you look back up into the problem, it doesn't give us an initial value. We need to come up with f of something equals something so that we can find the c. It's very simple, but not the first time we do this. The next time, I hope it's just so stinking easy for you, it's laughable. So what do you think? And even when I ask the question, sometimes it becomes obvious. We have to use this function up here. I should underline it because I'm recording this. Use this this series up here. What would be a really good x value to plug in for that?
0.
No. 1. Make it 0, right? 1 would be a great x to plug into this because it'd make everything 0. Wouldn't it make everything 0? So plugging in 1 would make every term 0. That'd be a great point to use, wouldn't it? Isn't that kind of obvious when I point it out? Just make all those terms 0. They'll all go away. So if your series happened to be 4 plus 6 x minus 1 minus 10 times x minus 1 squared, well, now f of 1 would just be 4. And you'd have this really, really nice point. Just make all those terms, or as many as you can, 0. All right, so we have our point. 0 is equal to the natural log absolute value of, let's see, 2 times 1 is 2 minus 1 is 1 plus c. So c ends up being 0 in the end. But we didn't know that until we got our point. Natural log 2x minus 1 is the answer for that. There you go. I'll show that.